surely they've asked this, but no one's told me.
Mm-hmm.
Should we Google it?
This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. Today we're going to do cosmic queries. And this time my special guest is friend and colleague, Matt O'Dowd. Matt, how you doing, man?
Great, Neil.
How you feeling?
Yeah,
all right.
real well.
Been too long.
It's exciting.
And of course we got Chuck Nice.
What's
Chuck and baby.
happening? Matt, good to see you.
Chuck, there's no cosmic queries without you reading the questions.
Now, there is.
There is.
There truly is, but I appreciate that.
So let me catch up our audience to the few of them who might not know who you are. So first, you're a professor and science communicator, so in the same business in that part of your life. And you have a PhD in astronomy and astrophysics from the University of Melbourne.
Oh.
Did I pronounce that right?
Melbs, as we say.
Melbs.
Back home.
No, I'm not going
Melbs.
there.
Yeah.
No,
We
that's
abbreviate.
that's too intimate. I'm just
For you, Neil.
University of Melbourne, Australia.
That's right.
And you're into all the stuff that I like most about the universe. Extragalactic astrophysics, everything that's happening beyond the Milky Way.
Right.
Quasars, active galactic nuclei.
Mm-hmm.
These are badass galaxies that have supermassive black holes in their core.
Right.
Just into that. You're also associate professor at the City University of New York at Lehman College.
Exactly.
Up across the street from my former high school.
Mhm.
Oh.
Yeah.
The Bronx High School of
Bronx High
Science is
School.
on one side of the street, and Lehman College is on the other,
Nice.
separated by a field,
Oh,
an
okay.
athletic field.
Oh, they had to keep you guys apart? Is there some kind of beef between
No chance
the
of my
college and-
people taking over the athletic field. The Bronx High School of Science is not that kind of place.
Oh, that's hilarious.
And you're also affiliated here in our Department of Astrophysics as a research associate. But I think most people who know you as host of the PBS, it's a YouTube program, Spacetime.
Exactly
Oh
right.
my gosh, what a following that has.
Yes. And
Sure,
a clever
we
name.
busted through 3 million subscribers
3 million.
just the
Wow.
other day. Yeah.
Ooh, well, congratulations
Who would
on
have
that.
thought?
Congratulations. I think
That's
YouTube gives you a little memento for that.
We
Yeah.
got it at 1 million, the gold button,
Yes.
which,
yeah.
by the way, it does nothing when you push it.
Oh,
well,
At least
nothing
that I know of.
that's what you know.
That's
Spent a lot of
right.
time.
I was going to say, yeah. Every time you pushed it, somebody's computer exploded in their face.
All right.
So, let's compare notes because we're both in the same business, if you will. So you brand yourself as a science communicator, but not a science teacher. So how would you divide those two tasks?
Well, I do teach and communicate, so I see the division.
Yeah, how do you divide?
I teach a nice astronomy class each semester at
With the
Lehman.
textbook and
homework
homework and
Right.
exams.
Exactly.
Okay.
slideshow.
Right.
Yeah.
Pop quiz.
Exactly.
Okay.
Yeah. Which is really fun. I mean, you don't get quite the intimate contact when you're staring at a camera and pretending it's your audience, right?
Right, because you have to
But
pretend
here
that there's a human on the other side of the glass.
Right.
Right.
Yeah.
Unless you see humans at all times.
Sure,
That's
no
a
matter
different-
where you go.
That's a different diagnosis.
Even when you're alone, you see a human.
Yeah. There's
Just
this
put them in
there's this
front of the
point
camera.
in the like 10 seasons of Space Time where you can kind of tell where I started to do that. A friend who's like an improv champion gave me this advice. Just imagine it's someone you know. And I became so much more natural as soon as I was doing that. I was talking to this,
Yeah.
just imagining that it's my mum or, my girlfriend or whatever.
Right.
Anyway,
So what you're saying, the early episodes, you were a little stiff. You were like delivering information rather than hanging out with the person in the,
yeah,
in the
I
camera.
was thinking exactly what my hands were doing, and it was uncanny valley.
Oh.
Don't go back to those. Anyway,
Okay.
but yes, to get
Okay.
back to your question.
Ignore his first 9 seasons.
Exactly. Yeah. This was just last week, actually. But no, talking to real students and having the interaction in real time is great. So I teach classes, and
you get feedback.
It's a very
Plus,
different thing.
if you say something that befuddles them, they'll look befuddled.
And there's such you can get away with more when you're talking to the camera because there's no immediate accountability.
Right.
In the classroom, there's accountability every single lecture. So when I first started, proper professor lecturing, my mood at any time was completely based on how the last lecture had gone. Like if I flubbed the lecture, I would feel like crap until the next lecture. And if it was amazing, then I would be on top of the world. So there's a lot of there's this feedback.
Yes, exactly.
Yeah. Oh yeah. But it's also, the stakes are high, because if you don't get it right this class, then next class they'll be lost from the beginning. Right. So you're building this.
You leave them behind.
Edifice of knowledge, and you have to do it right. Right.
And how do you know that they're just not sitting there glazed over it, receiving all the information and not really processing it?
Well, if they're glazed over, that's a hint. And so then you have to
know that they're glazed over.
Yeah.
For
part of your
reasons,
social skills is to be able to read that.
To some extent. And one trick is there's always a few kids who are so into it that you can be totally teaching to them and lose everyone else.
Suck-ups.
So, always sitting in the front. They bring an apple every class. Yeah.
Just kissing his
God
butt
bless
all
him.
day long.
So,
and if you're one of those, thank you. Thank you so much.
So which astronomy, how much math is in that intro astronomy class?
Wow.
This one is not much, okay, because it's at CUNY you got to take a science class.
CUNY
and
City University in New York.
Yeah, exactly. So you got to take a science class, and so there are people with all sorts of trajectories who don't have a lot of math otherwise. So I've pared it back semester after semester until now we have, like, if I teach them a core mathematical concept, they come out with one big intuition. And for this class, it's like the nature of proportionality and, so understanding why these equations are what they are without having to solve too many of them.
Mm-hmm. Yeah, because there are people who think astronomy is just looking at pretty pictures.
Right.
Because that's how the press delivers images from the James Webb Telescope, from Hubble. And no, behind closed doors, we got to figure this stuff out.
It ain't Instagram. You know what I mean? It's like Instagram for science.
It was shocking when I discovered that it wasn't just taking pictures through telescopes.
Yeah.
So just today, my assistant brought to my attention some paper mail, not email.
Wow.
Paper.
Snail mail.
Snail mail. And it's right here. This is 2 letters, one from a 10-year-old and one from an 8-year-old.
Wow. Look at that.
See that? See that?
Wow.
Look at that.
Those are real. All right.
And
handwritten letters.
And this, I know this is Cosmic Queries,
Yes.
but I don't think they're Patreon members.
Well, they don't have a job, most likely. I'll read them only because I know that they're probably unemployed. But I will tell you this much. Let's see. One is from Dexter, and the other is from Abby. And Dexter and Abby, I'm going to let you know, you owe us $5. And the moment you get a job, you need to join Patreon and send us our money. Okay? Because you have cut the line and you have displaced many people who take their hard-earned cash and send it to us so that they may inquire of Dr. Tyson the wonders of the universe. But you think because you 10 years old and cute that we're just going to do whatever you... Well, I got news for you. You need to get a job.
I think they got the point.
Okay,
Chuck.
yeah.
You think they got the point?
Actually, at some point there, I morphed into talking to my own children.
Get a job.
You will not just lay around this house.
You're 5 years old.
Exactly.
So you pick one from each.
Okay.
Let's see.
All right, here we go. All right, let's go with Dexter.
Okay.
Who's coming from Middletown, Maryland, and he says, "Dear Mr. Tyson," or should I say, "Dear Mr. Tyson"? Okay, I'm not going to do that. Because if he's watching, he's going to be like, "Chuck, you know what? You're a real a-hole."
No, he's going to say, "Chuck, my
Wouldn't that
voice is
be
deeper
fun?
than that."
I'm like, "Dear Mr. Tyson." I don't know what his problem is. Anyway. He says, "Dear Mr. Tyson, my name is Dexter. I'm 10 years old, and I have a few questions if you have time to answer them."
But we're going to take one of them.
Okay, we'll only take one. By the way, let me just say to Dexter, your handwriting is impeccable, and it's cursive.
It's in cursive. Nobody. Yeah.
He's a 10-year-old in cursive.
Okay. What planet is he
Do
from?
you see this, Matt? Look at this.
What planet?
What planet is right?
I didn't know they taught kids to write anymore.
I don't write at all. It's just be emojis, row after row.
Yeah.
All right.
Okay.
You pick one. You're the man.
I'm going to say I want to pick because many of them are personally. Okay. Here's what I'm going to pick the last question he asked because he asked a lot of great questions. I want to read them all, but here's the last one. It's the fourth. He says, "Finally, why do you want to die by jumping into a black hole? I mean, it sounds awful. What would it feel like? What could you actually learn?"
Oh, yeah. So he might have heard something I said at some other time about this. It's not that I want to die by falling into a black hole. Is that if I'm going to die and I could pick, I would pick the black hole.
Okay.
Instead of getting hit by a bus
Right.
or laying up from some disease.
Right.
If somebody said you're going to die tomorrow, I'm picking a black hole.
Right.
Okay? Because how many people get to tell you what happens while they're falling into a black hole? I'd be the first person sharing that information.
That's true.
Wait, who would you tell?
Well, so whoever's listening,
That's the problem with the black hole. Isn't it? It's like
I need like a tin cans and a string or
A
something.
long cord that comes out.
Look, so my signals will get redshifted as I get closer to the black. You're a black hole man, right? So my signal.
I'm dubious.
You don't think I could pull this off? So I would send signals as I descended, but those signals would get shifted by the gravity difference between where I am and where you are receiving my signals. So we'd have to figure out a way to make that work. But I would be broadcasting the entire time until the tidal forces ripped me apart.
Right.
Now, it would first rip me apart at my midsection. You can calculate that.
Right.
When the tidal forces exceed the molecular forces that hold together your flesh.
Mm-hmm.
Now, if I'm broken at my midsection, I probably am still alive.
Yes.
Because all my organs, my vital organs
they're
up here, and my brain. So
Sure.
I'll probably stay alive for
Fine.
my intestines will be hanging out.
You're also a little thinner because of the spaghettification.
Yeah, I didn't get there yet. I didn't get there yet. So the intestines will hang out, but you don't need your intestines.
Right.
In
Because
your
you're
final
not going to
moments
have
of
a
life.
meal in the black hole.
Exactly. Right. Okay. So the intestines will spill out, but my heart, lungs, all right. But then those two other parts would snap into, become 4 pieces.
Right.
And then 8. And at some point, it's just my head. Okay.
All right.
And then after that, my head splits. So he says, how would that feel? It would hurt. What do you think? But also, as Matt made sure I included here, I'm being funneled down into a narrower and narrower channel through space-time.
Mm-hmm.
So not only am I being stretched head to toe, I'm being extruded through the fabric of space.
Like toothpaste.
Like toothpaste through a tube.
Right.
And we have a word for this.
Mm-hmm.
You should be impressed with the English language for how many words we have for how to die. And one of them is spaghettified. I get spaghettification.
Oh, that's the most delicious way to die. Spaghettification.
Yeah. Anyhow, yes, it would hurt, and I would be stretched apart. So, what would we learn, Matt? Is there something to learn if I get close to a black hole that you can't figure out theoretically?
First up. So my favorite type of black hole is the supermassive type. Okay,
Oh,
the type
Not just the massive black hole.
type.
No,
The
super.
supermassive.
They're a little smaller than the super duper massive, but bigger than the intermediate. Anyway, those ones are so big, like they can be the size of our solar system. You don't get spaghettified until you're deep in the interior, so you can
Right, you'll
cross
fall
the
through it
event
for a
horizon.
while.
I'd be able to talk about
You're
it.
totally
right.
fine. Totally fine. I mean, you still get the redshift, so those waiting might have to wait the entire age of the universe to get your message, crawl out of that black hole. But you would witness it yourself, and you would know. You'd be able to tell yourself the story about what's inside a black hole.
So once I'm inside the black hole, I'm alive because I'm not spaghettified yet.
Right.
The
Because
supermassive
you're
those
just
one.
cases.
falling towards
Exactly.
Towards the singularity.
singularity.
And I would be enlightened to myself.
To yourself.
Right.
What would happen, but that's about it.
Yeah.
Oh
you
man,
can-
and that wouldn't have.
but you got to
that-
die some way. So.
That would be almost worse because you would have all this knowledge of the only person who's ever seen a black hole,
Yeah.
and you wouldn't be able to tell anybody.
Yeah.
Depends how selfish you are, really.
Yeah.
For me, I'd rather tell people, but if it's just me,
Yeah,
I still
it's
want
good to know. It's still good to know.
Yeah.
Hello, StarTalkiverse. Neil deGrasse Tyson here, your host of the StarTalk podcast. I'm here to announce that we just opened a brand new channel on YouTube called StarTalk Plus. And that's where we're going to bring all kinds of innovative content that doesn't quite fit on our flagship channel, but they will involve experiments in what we create, what your reaction might be to what we create, and it's going to be our skunkworks, as it were, to borrow a term from aerospace. So I look forward to sharing all of this new content with you, and check it out if you have a chance. All right, so Chuck, you got Abby there. What do you have?
Oh, this is Abby, and she's 8 years old. She says, firstly, what has been your favorite discovery so far? And what do you predict they will discover in the future? Ooh.
All right, Matt, that's going to you.
Wow. My favorite discovery.
Yeah.
Not of mine, because those are
Yes, of
a little
yours.
crappy. I thought, historically.
Oh, no, your favorite. This is a personal letter, handwritten.
Wow. I found some pretty cool gravitational lenses that
Okay, that's geeky.
that are pretty awesome. Yeah. So at this point,
So a gravitational lens would be a mass in the universe that sits between you and something behind it, and the light from behind it got lensed. What makes one lens better than another?
okay, so
By the way, I'm old enough to remember the very first lens discovered. That's how old I am.
Wow.
Yeah, we were losing our shit.
yeah.
Yeah. Sorry. She's an 8-year-old child.
8-year-old kid.
Sorry, it's a grown-up show.
Right.
So we think of the universe as, the light comes to us, it follows straight lines, and wherever you see a star or a galaxy or whatever, that's where it is.
Mm-hmm.
That's not the case. Okay, the universe is wibbly wobbly, so there's gravity everywhere that makes this space like this stretchy fabric, and so light travels by these slightly wiggly paths. But sometimes, if there's a big mass like a galaxy lined up, then the light can travel multiple paths from some distant object, like one of these giant black holes, to us. And so instead of seeing one, we can see many
images of that
Many
one
images.
object.
Of that one object.
Yeah.
So why do you have a favorite one? They all sound like they look the same after a while.
There are some that are just you would call them golden lenses because just
more
everything's
photogenic.
lined up. They are more photogenic. Everything's lined up so perfectly that we just see amazing stuff. Like we there's this the one of the was it the first one, the Einstein cross?
Yeah. That's
Yeah.
early. That was early.
Yeah.
Uh-huh.
That one's really cool because the lens is really close to us, and so everything that's happening happens much more quickly. So we see the quasar flickering really quickly as the stars in that lens move around, and we can do really cool stuff. We can essentially map that distant black hole by looking at how the thing flickers. And
You know how we first discovered that it was an actual? So a lens, we have two images of a quasar.
Okay.
Initially, there's just two different quasars.
Right.
Until someone discovered that a variation in one quasar
Was the same
was repeated
exactly.
in the other.
in the other quasar, but with a time delay.
Oh, look at that.
Okay, so it meant the two path lengths were different. And it was like, whoa.
That's
and everything that changed matched.
That's really cool.
So it was the same object.
Yeah.
Yeah. And
We freaked out.
Yeah,
I mean, in a joyous way.
Yeah.
That's how old I am. Back in my day, we discovered Earth, the first planet.
First, we thought it was a copycat quasar. Playing Simon Says.
and we did. We thought these could be like binary quasars.
Yeah, there was a whole lot of first thought about
Right,
it.
right,
So,
right.
Because no one's seen a lens. Why would you? That's not your first thought.
Einstein knew that his theory predicted these lenses, general relativity, but he didn't think it would ever be seen
Right.
because it was such a small effect. Same with gravitational waves. And then we built some pretty good telescopes.
Yeah, better than he imagined. So what's the second part of that question?
The
What's your
second
favorite
part
discovery?
is, what do you think they'll discover in the future?
Yeah. Give us your best prediction.
One thing that you can do with gravitational lenses, I'm on the bandwagon today, with this whole time delay thing. So you see one change and you see the other change. This lets you measure the distances to these galaxies, to the quasars, and that's one of the hardest things to do in astronomy, as I'm sure you know. Like, we discovered that the universe is expanding by looking at these fluctuating stars in Andromeda and more distant. And now we use supernova explosions to try to get the distances to more distant galaxies. And all of this showed us, for one thing, that the universe is expanding. Okay? If we track the size of the universe looking back through cosmic time, we see that it's expanding. But we also see that that expansion is accelerating dark energy. Okay, that's what the supernovae showed us. But so we have no idea what dark energy is. But if we have a way to track the rate of expansion over cosmic time to the greatest distances, then we can see if dark energy is the thing that fits into Einstein's equations in the kind of most simple way, the way that Einstein actually wrote it himself, the so-called cosmological constant, or if dark energy is changing over time. Okay, in which case it could be something really crazy. So we can use these time delays to figure out what the hell dark energy is. And this is, I would say, one of the most...
You're giving all this hypothetical. We might see it. It could be. The kid wants to know what your prediction is.
My prediction is that that what dark energy is one of the biggest unsolved questions, and one that we really have a hope of finding. So knowing what dark energy is, I'm going to say. It could happen.
Okay, that's a prediction. That's a prediction. We will find out.
Next year, 5 years, 10 years, 20 years?
One of those. One of those. Yeah. I mean, that's the thing with science. You just don't know. You don't know which experiments are going to pan out.
Yeah. All right. So, Chuck, let's get straight to the Cosmic Queries.
All right.
Patreon edition.
For the, not the freeloading kind.
Freeloading kind.
We'll do the real Patreon people. Okay.
We're going to find out that Dexter and Abby had to go to therapy after listening to your...
No, those guys are the best. 8 and 10 years old and listening to this show.
Yeah,
I mean that's impressive enough. Yeah, that's outstanding.
And one of them said their favorite show, the favorite variant of this is
Explainers.
Yeah.
I mean that kid is pretty advanced.
Yeah.
Way to shame all the other kids out there. I like that.
All right, what do you have?
This is Kylie Ronning. Kylie Ronning. Dear Neil, Matt, and Chuck, I have been waiting for this moment for so long. Thank you for reading my question. I'm wondering if you think it is possible that there is no such thing as the smallest particle, and that we can zoom in on matter infinitely. The Big Rip theory assumes that there is a finite end to the universe's ability to stretch out. Why do we assume this? And what if this assumption is wrong?
Man.
Look at that.
That's so easy. I'm going to let Matt take that one, okay? I don't want to. This book is beneath me.
Exactly.
Yeah, Matt.
No, this keeps me awake at night. This whole idea of is there an end to scale? Like, is there? So we have this idea that there is a sort of smallest measurable distance, the Planck length, right?
Mm-hmm.
So we can't do experiments that can probe space distances down
below. So the Planck length, remind me, that's the distance over which light travels in
a
Planck time.
Now, I'm calling.
That's 0.00000.
I'm calling BS. I'm sorry.
So
I mean, first of all, that is unfathomable.
Yeah,
you cannot conceive of that space.
That's why it's the Planck length. That's this.
Yeah, but you can imagine. All right, so you have this ruler and you break it down. So it's a meter ruler. Okay, break it down to a centimeter. Okay, now it's made up of millimeters. Break the millimeters down. Blah blah blah. You can go all the way down. Why is it that you have to stop being able to break it down into smaller
at a Planck length?
At a Planck length.
There's no more rulers. Why? And it's not. I don't think it's understood. Honestly, I think we don't know what the dimension of space even is.
Understood, or you don't think you understand?
No,
the it
no,
and the I are different things.
Yeah, yeah. I definitely don't understand it. And
Uh-huh.
I think there are others who have better ideas, but it's certainly not known.
Right.
It's certainly not
So
known.
there is an I in it.
So the limit comes from these combinations of these fundamental constants, like
Right.
the speed of light,
Right.
the Planck constant, the gravitational constant, and when you put them together in certain ways, you see, including things like the Heisenberg uncertainty principle, you see that it is unmeasurable at this scale. But there's no
it's
other
kinda-
reason besides the
Wait, just to be
value of
clear,
those constants.
It's unmeasurable well before then. It's just unmeasurable in principle.
principle, yeah,
just-
exactly.
You ain't measuring. You ain't coming near that
No.
with your
Yeah.
school ruler.
Exactly.
I have a protractor, so it has to work.
So
Anyway, so what happens when you try to subdivide even smaller? Then
okay, so maybe the Big Rip is a hypothetical thing. So at what point is anyone declaring that space cannot stretch?
So the big, I
with
mean,
the
so
expansion.
the idea if the space is space infinitely stretchable, the idea of the Planck length doesn't preclude that. So you could
Right.
take whatever's smaller than the Planck length and make it bigger than the Planck length, and then it's measurable. But it doesn't
After you've stretched it.
tear space to shreds. And so if the dominant theory of what happened at the Big Bang is right, which is inflation, so the idea that the universe multiplied its size by a factor of 10, like 60 times, then that's pretty stretchy. And so if it could do that, then the current pretty gentle rate of expansion isn't going to be a problem.
Oh, using past evidence.
Yeah.
to-
If inflation is right, which
That's right.
some smart folks believe.
Okay. Well, it's more fun to think we're all going to end in a tear
Sure.
in the fabric of space and time.
Right. And they're just going to get fat and bloated.
We'll just get
Just going
stretched
to
out.
keep
And will it
getting
sound like a
stretched
tear?
out
Yeah,
until we
yeah,
can't stretch. I mean, forever. Forever. Just continuously stretching.
Yeah.
Wow, that's a great
All right.
question,
All right, keep
Kylie.
going.
Way to go. Way to go with the
No
question
sleep
there.
tonight,
Nice. Very, very good. This is Jeremy Corbello. He says, hello, Dr. O'Dowd, Dr. Tyson, Lord Nice. This is Jeremy from Austin, Texas. Considering all moving objects in the universe are causing gravitational waves, as proposed by Einstein's general theory of relativity, can we mathematically accumulate all of the outward momentum from gravitational waves from the inner portion of the universe and use that to help justify the acceleration that we're seeing in the expansion of the universe vis-a-vis dark energy? Everything from the beginning of the universe has always been pushing outward, and every bit of gravitational wave energy would be accelerating that expansion. By the way, love the show. Okay.
That's a hell of that's a mouthful of
That's a
question right
lot,
there.
man.
Yeah. So it sounds like they're wondering, since everything makes gravitational waves, however small,
Right.
that these go out into the universe and form this pressure that we measure as the dark energy.
Yeah. I mean, I haven't heard this idea, and I need to think about it more. A couple of nitpicks is that, the normal way we think about the universe is not as it having a center and an exterior. So we don't have, it's not pushing out into anything. It's, it's either, according to the standard general relativity, it's either infinite and expanding, or it's this kind of closed volume that doesn't have an exterior. So there's no middle of the universe. There's definitely no middle of the universe to
push out.
To push out. So
So you can't think of it as like a cake rising in a pan.
you could try, but I don't think you'd get to the right answer if you did.
If you did that. Okay.
Yeah.
Just eat the cake and call it a day.
Just
So-
drown your
that-
sorrows in the cake itself.
That said, could gravitational waves do this for some of what the universe
Well,
actually is?
let's ask it differently. What is happening to all those gravitational waves?
Oh, yeah.
They
Because we measured it. It washed over us. We know that
Yeah.
it's happening. The black holes collided. We had the waves. So
I mean,
then what happens to them?
they slowly dissipate, right? As
Okay.
so they get weaker and weaker, but then they
Especially in an expanding universe, they'll get weaker and weaker.
even more. They get redshifted, etc. But they become part of what we call the gravitational wave background.
Oh,
Okay.
So there's this Very
I forgot about that.
right on.
Of course.
So it's everywhere. The ones we've detected are relatively nearby, big gravitational waves, but black holes have been merging since the beginning of time, close to.
There's a background din.
There's a
of
background, just a
gravitational
little
did
wiggle,
not
wiggle, wiggle,
know.
wiggle,
Can
wiggle.
we talk about this? Because this
No,
is the
we
first
can.
I have ever heard.
Right. Well,
Right. No, I knew about it. I forgot to connect
So
the
you know-
dots.
Background
I forgot to connect the
gravitational-
dots.
And
gravitational
the-
wave background.
the coolest observatory ever I'm not going to say built because it wasn't built, but invented, is looking for it. Conceived, which is the pulsar timing array, which is just the most awesome thing in the world.
This is not using pulsars across the galaxy, carefully timing them and watching waves move through your line of sight, changing the pulse rate that you had so carefully measured.
Exactly.
And that way you can track gravitational waves going bump in the night, even if they don't come across
Like galaxy-sized gravitational
This
waves.
is
Galaxy-sized
so crazy.
gravitational.
I get shivers
every
okay,
time I
so
think
now
about it.
I'm going to be honest because you lost me. Let's go back. You're tracking what, the spin of the pulsar, or what?
Yeah,
what it's the spin of the pulsar.
So pulsars are these exquisite cosmic clocks. They're the cause of dead stars that weren't quite massive enough to make black holes, but
right.
they spin incredibly rapidly
Right.
and
and
very
very
precisely.
precisely.
and very precise.
Yeah.
Yeah.
And so and they also shoot out these beams of particles that sweep by the Earth, and so we see this
Okay.
much
Right.
faster. And so we see these across the galaxy.
That's right. If they were simply spinning, you wouldn't.
You wouldn't be able to do it.
Yeah,
You would
they
have to
also
have something
process.
spinning off of them.
Yes, yes.
For you to see the difference in.
In fact, it's more than that.
Okay.
So it's not just particles and energy being spewed out the poles of the axis.
Right.
The spewing part is actually tipped relative to that.
Gotcha.
So as it spins on its axis,
Right.
this
So
other pole
it's even
swings
better.
by. It's
That's
even better.
That's a better
And and
gauge.
this is the
That's
beacon.
a better gauge of the spin.
Like Earth's magnetic pole doesn't align with our spin pole.
right.
If we had one of these, it would spin around.
Okay.
Every day, you'd see this beam.
This makes great
No,
sense.
it's great.
This
It's great.
is- this
Okay,
is-
so keep going.
Yeah, so
So did they
in some
name-
cases like 1,000 times a second.
Yeah.
And so we see just slight variations in the tick, 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 that are correlated across the galaxy. So a little lag here that becomes a little lag here that becomes a little lag here, and we can
Watch it
reconstruct.
Right.
We can reconstruct
speed
these
of
waves.
At the speed of light.
Oh my gosh.
Right.
Exactly. And so recently there was the first, tentative but still pretty intriguing detection of the gravitational wave background and how big it is. And so, could that gravitational wave background be dark energy? I don't.
That was the question.
know. I don't
That's
know.
basically the question.
The answer is I don't know. I surely they've asked this, but no one's told me.
Mm-hmm.
Should we Google it?
That's awesome.
All right.
Well, there you go.
So we don't know.
Yeah.
we
That's the
don't
answer.
know.
Yeah,
Okay,
yeah.
Jeremy, what a great question. That was enlightening.
All right.
That was my pulsar joke. See. All right, never mind.
Enlightening.
See,
I get it.
Okay, never mind.
Yeah, you had to
All right,
actually
I'm gonna
explain
have
that
to-
joke, didn't you? Okay.
Seriously, when you got to explain them,
It
you
ain't
know
a
they're
joke.
not working. That's all there is to it.
Ain't a joke. Have you ever wanted one of your questions on the universe answered? We all have questions about the universe. From black holes to quasars, quantum entanglement, wormholes. There is no end to the depths of cosmic curiosity. Well, the entry level of Patreon membership with StarTalk gets you just that. I think it starts at $5 a month. You have access to the question line that reaches our Cosmic Query programming. And not only that, we produce a special Cosmic Queries installment just for Patreon members.
So if you weren't the director of the Hayden Planetarium, what do you think you would be doing? What?
Okay, but this had to be another universe. It wouldn't
All right.
happen in this universe.
Okay.
I'd be a songwriter for Broadway musicals.
Ooh!
So that's the entry level, and the perks ascend from there. There's a level, in fact, where we send you an autographed copy of one of my latest books. Right now, it's Starry Messenger, Cosmic Perspectives on Civilization. And it's signed with my fancy fountain pen with purple ink. So I invite you to just check the link below. And all of that money goes to our ability to experiment with new ways of bringing the universe down to Earth. So thank you for those who have already joined, and we welcome others to participate in this grand adventure of what it is to bring the universe down to Earth. As always, keep looking up.
All right, this is Town Poem. Hello, world. This is Jesse from West Virginia. Is there any correlation between the increasing amount of space being compressed in the interior of black holes and the increasing amount of space stretched by the expanding universe? Kind of the same, but here's the difference. Could radiation and dark matter be thought of as counterparts? Since radiation is a wavelength without mass and dark matter is a mass without wavelength.
Oh.
What?
Whoa.
Since radiation is produced by matter interacting with radiation, could dark matter be produced by matter interacting with mass? Ooh.
Man.
Damn, these
So there
people
was-
are.
Where do these people come
Where
from?
are they coming from?
What?
That's like 3 questions in a row where they're just like, yo, man, I'm gonna make sure you went to school on this. Like, I gotta make sure that your degree is legit. Here's a question.
So there was a paper on the first idea that was pretty recent.
A research paper.
A research
published
paper
by scientists, peer-reviewed.
The first paper was in the 60s and was by a Russian physicist named Gleiner. And he had this notion that there could be this coupling between the interior of the black hole and cosmological scales, right?
Okay.
And so Gleiner was this sort of forgotten genius, and it sort of got forgotten. But there was a recent paper that sort of tried to resurrect it and to argue that this coupling between the interior of the black hole and the cosmological scale, by what mechanism I don't know, would lead to this global negative pressure. And negative pressure is what you need to accelerate the expansion of the universe. And crazily, I actually read these papers, but I don't remember why I strongly objected to them.
Okay.
But I do remember objecting to them.
Okay.
I don't think there was a meaningful mechanism to have that communication between the scales, right? Interior of a black
So
hole.
you're just
and the
asserting it as a plausible.
No, there was
account
like a
rather than-
there was like a loose interpretation of general relativity that I thought was unjustified. So
Okay.
I thought there was a slightly crappy interpretation of GR.
Right, just say it. It's crappy.
Yeah, it's crap. Okay.
Yeah, like it felt like, looking at the
From one colleague to another, your work is crap.
yeah, I didn't buy it.
But
We
that's-
did
I mean,
we did
isn't
an
that- that's-
episode.
Right.
We did an episode on this
Okay.
actually. So
But that's
Of
your
space-time.
that's-
yeah, of space time.
Isn't that the whole, that's the whole crux of
That's the whole-
science,
that's the whole
right?
point.
That's the whole point.
Yeah.
Is for you guys to hate on each other's work. Just you worse than rappers, to be honest. Scientists are worse than rappers. Just like, oh, you think you good? You think you
You think you solved this?
You think you solved this? How about this? Your work is crap.
Yeah, this is the scientific method.
Yeah, exactly. That's pretty cool, though.
So Chuck, we only have a couple of minutes, so maybe we can speed up our
Oh.
answers and we can. Okay.
All right, here we go. This is Gina Martin. She says, hello, smarty pants. I was wondering, since space is expanding, what is filling in the gaps? Is matter being created to fill and expand our universe volume? I've heard space compared to a balloon is expanding with dots on the surface. Oh, the old balloon, right? But a balloon is only able to expand if something is put inside of it. So what exactly is inside of our universe that's making it expand? So I love it. These people are like taking all the examples,
Yeah.
like, the rubber sheet and the balloon and all of that. And they're just like, yo, man, what's the deal? Like, what's inside?
I don't know. I think it's possible to extend the metaphor too far. And that might be what's happening here.
You've gone too far.
There you
I
go,
think-
Gina.
I don't know if
Gina,
there's-
you're the problem. You're the problem, Gina. You went too far. You went too far,
Well,
Gina.
I can say, because I'm old, I'm the senior member here.
Yeah.
Back in my day,
Right.
well, we knew the universe was expanding. We didn't know whether it would one day recollapse.
Okay.
Okay.
Right.
Plus, there was no direct evidence for the Big Bang
Okay.
because that's how old I am. Okay. At the time, Fred Hoyle said, "I get it. We live in an expanding universe, but I don't like the Big Bang." In fact, he named it the Big Bang pejoratively,
Right.
Oh.
and then it stuck.
Yeah, look at that.
Okay.
Wow.
He said, "We want a Big Bang."
Right.
Copped an attitude about it.
That's a big bang.
Right. And then it stuck. So he hypothesized.
Like Obamacare.
Right. Now we own it.
So the problem was, if we're expanding, how do you keep the universe approximately looking the same at all times?
Right.
If you're expanding.
Okay.
Okay. So he said, hydrogen molecules are being hatched into the expanding vacuum. And those molecules then create clouds and then form new generations of stars.
Wow.
So if that were true,
Mm-hmm.
you'd be able to see new galaxies being born today
Today.
or at any time.
Right.
But we didn't.
Right.
All galaxies are approximately the same age.
Ah.
So it's a steady
Wow,
creation
that's-
of matter. He just
Ooh.
hypothesized that.
Right.
But people said to him, how is it that you can just assume matter is popping in out of nothing? That's crazy. And he said, is it any crazier than you popping the universe into existence out of
Out
nothing?
of nothing?
And that shut everybody up.
Right.
He was a smart guy.
He was still
Yeah.
wrong.
He was still wrong.
Still wrong.
But he knew how to shut people up.
Yeah, no, but I'm just saying, in the day,
Right.
this idea that matter is being created in the vacuum,
In the vacuum.
the expanding
Yeah,
vacuum.
I mean, this is like our how much can you stretch space thing, and the answer is maybe infinitely. But there's also no interior to the balloon in the case of
Right.
our universe.
there's
There's no
right.
analogous interior.
Right. So there you go. Wow, that's pretty cool, man. All right, this is
A couple more questions, and we can even speed up our answers. Go.
Okay. This is Euclid A. Loguidice, who says
His name is Euclid.
Great name.
Euclid
Okay, I'm afraid
Euclid
now.
A.
Based on those other 4 questions. we had.
Loguidice is the last name. Aloha, Dr. Tyson, Dr. Dowd, and Sir Nice. It's Lord Nice, thank you.
Lord is above sir. in
Lord
case you
is
didn't know.
above Sir, just in case you didn't know. Euclid here from the Big Island. I tried asking this question before. Not sure if I missed the deadline. There's no, dude, relax. There's no deadlines, okay? You're okay. All right, here we go. Could there have
But
been...
the Big Island, he's from Hawaii.
He's from Hawaii.
Hawaii,
That's
Big
right, the
Island,
Big
yeah.
Island.
Where we have our big telescopes.
Good ones,
There
yeah.
you go. Could there have been much more massive clouds of gas and dust in the early universe with strong enough gravity to cause supermassive black holes to form rather quickly? So that's your deal, man.
Yeah, I feel like
That's all you.
I feel mildly qualified for once. The answer is yes.
Okay.
So there is a big mystery, especially with JWST, the James Webb Space Telescope. We're seeing these quasars in the early universe that are powered by these black holes that are just too big. Okay, these things had to grow, and they had to grow by either eating gas or by merging little black holes into bigger ones. And so the ones we see back there that are a billion times the mass of the sun, there's no way that in our current understanding they could have grown that big. And so a lot of people have been asking, how did they start? Was there some crazy mechanism by which they could just gobble up all the gas super quickly? Did all these black holes form near each other and then fall together? Or did supermassive black holes spontaneously form? Or at least, if not supermassive, the one tier below it, which is intermediate mass black holes. So there are ways to collapse clouds of gas directly into black holes. Normally what happens when you have a giant cloud of gas is it starts to collapse, but then it fragments, it breaks apart, and it forms stars, right? In the early universe, the gas was, let's say, more pure. The thing that makes gas fragment today is that it's polluted. It's polluted by
Enriched.
All right.
Oh, look at that.
We're made of that
Let's be
stuff.
positive.
I'm
Yeah.
saying enriched.
Yeah.
Okay. He's talking about
Right.
oxygen,
Yes.
carbon.
Right.
Yeah,
So
all
all
that
this
stuff.
stuff. So all the other novae, or is it novae?
Supernovae.
Yeah,
Supernovae.
and those
has-
elements cause these clouds to cool down too quickly, which causes them to fragment. But in the early universe, it was just hydrogen and helium. None of these elements had been made because there had been no stars to make them.
Right.
And so the clouds cool down very slowly, which means they could hold together as they collapsed and not
Make
fragment.
one giant mass.
One giant
exactly.
mass.
And when you get
Wow.
it's like if it's a million solar masses the size of our
By the way, this
Solar
answer is not
system.
shorter as it should be. Okay.
well, cut the crap then. So the answer is there. Some people think so. Some people
Yeah.
think these things
Okay.
could have formed.
By the way, that's fascinating. Yeah.
Thank you.
All right, slip in one last one.
One last one.
Okay, 30-second answer.
30-second answer. Okay. This is Bogart Dieter. Okay. I think it's Bogart Dieter. Hello, Professor. I'm hailing from Belgium. Could you please describe Planck second by Planck second on a quantum scale? What happens the moment a black hole event horizon is created? So he wants you to, step by step, give us the breakdown of the event horizon
in the next 30 seconds.
In the next 30 seconds, which, I mean, measured by Planck seconds.
Can I talk that fast? So black holes these days are created by collapsing cores of dead massive stars. And the first thing that happens is that the supernova occurs, which results when the core collapses into a neutron star. Most of the stuff gets flung off. The neutron star, if it's big enough, will shrink. The bigger it is, the smaller it ends up. But at some point, a virtual event horizon forms in the core. And it doesn't really exist, but it grows. And if the black hole, if the neutron star isn't too big, then the virtual event horizon doesn't quite reach the surface, and it's a neutron star. But if it is big enough, then as the neutron star shrinks, the virtual event horizon expands, and when they meet each other, it becomes a black hole. Okay, the escape velocity at the surface becomes the speed of light, and in that instant, everything goes dark.
Whoa, that is pretty damn dope. So that's cool. So the event horizon is actually born within and then expands out.
Well, the Earth has a virtual event horizon also. It's about 1 centimeter in diameter at the core. And it's not real. It's just how much you would have to crush the Earth down.
To get down to that
It's only
point.
about the size of a plum. I did the math on that. If Earth were a black hole.
I've been telling people it's a centimeter. Holy crap. I have to contact a lot of students
Maybe
if that's wrong.
Maybe that's a really tiny plum.
I think it's 9 millimeters. But is it diameter or radius?
So 2 of those, so 2 centimeters is a little closer to a plum. Have you been telling them that's the diameter?
I think it's the diameter.
You've been telling them it's the diameter.
Oh no, it's the Schwarzschild radius.
Yeah, no, I get it. So
No, you're right. It's the radius.
the radius. So 2 of those gets you 2 centimeters. That's about
Small
like
plum.
that. Yeah, small plum, about an inch.
About an
a little
inch.
less than an inch.
Yeah, about an inch, yeah.
I was getting a plum.
Look at that.
You're right.
Ooh.
That's pretty cool, man. Yeah. So that's still a cool thing to think about. Is that?
Crazy,
yeah, that's just mind blowing.
Yeah.
Yeah, so every object has its own virtual event horizon. If
Right.
you collapse within that, you're a black hole.
You're a black hole.
And you ain't coming out.
Yeah, exactly. So, yeah. Are there any, okay, because I know you need a certain mass in order to actually achieve black holeism, okay? But
density.
Density, not right. So, because the mass itself has to go down to a certain density to create that. But are there any localized black holes that, like we have clusters? Do we have black hole clusters? Like
Yes.
Yes?
Crazily, we do. At the center of our galaxy. And so this has been hypothesized for a long time because we think that because black holes tend to be a bit denser, they just as dense materials fall to the bottom of whatever material, they slowly trickle into the center of our galaxy. And over the billions of years, the inner core of our galaxy, the black holes, should have ended up in the center. Okay, so you can do these dynamical calculations that show that. But there were recent observations with, I think it was the New Star X-ray observatory.
New Star is a telescope, NUSTAR.
That saw them. So it took these X-ray images of the core of our galaxy and saw these bright spots, too many of them. And so we do expect there to be this swarm of black holes in the core of our galaxy.
Damn.
Like thousands of them.
That's amazing.
Yeah.
Avoid the galactic center.
Avoid.
Avoid the
Yeah,
galactic
detour.
Yeah.
Guys, this is great. Thanks for enlightening us.
Absolute pleasure.
I'm sorry.
You enlightening us. Not guys, thanks for enlightening us. Matt, thank you for enlightening us.
You really made us laugh.
But I'm reminded that with the power of math and knowledge of the laws of physics, that we're not limited by just what you can see. We're only limited by what you can think. Which brings the question, is there a limit to how far the mind can go in the universe? How far beyond where we can physically travel, can our mind take us? That's the real future of science.
Wow. You just came up with that shit on yourself right then? Okay.
This has been StarTalk, Cosmic Queries Edition. Of course, all about the universe. Until next time, keep looking up.